In this lesson, we'll learn how to do the calculations for a two-sample t-test using Excel. This is by your old Uncle Frank. Before we do this problem, we'll actually start with a problem to show you how to do this. We'll start with the following problem. Does the forced expiratory volume for 1 second for patients with coronary artery disease differ between these two clinics? We'll assume that these are random samples from the patients in Clinic A and for the patients in Clinic B, and we'll do the formal 7-step hypothesis testing procedure to test to see if there is a difference. Now, I always start out with step 2. So we'll start out with step 2. Step 2 is the alternative hypothesis, or what it is we're hoping to show. And we're trying to show that the mean for Clinic A, the population mean for Clinic A, is not equal to the population mean for Clinic B. That is, that they differ in some way. Our step 1 is our null hypothesis, or HO. And our null hypothesis is everything else that could be true if step 2 is not true. So in this case, our HO would be that the population mean for the patients in Clinic A are equal to the population mean of the clinic patients in Clinic B. Step 3 is just to set our alpha. So we'll set our alpha at 0.05. We set it at 0.05 unless we're told otherwise in this course, because 0.05 is just so traditional. Step number 4 is we set up our rejection rule. Our rejection rule will be to say reject HO if. Now let's take a look at maybe a picture to get an idea. Here, since we're talking about different, we will reject the idea that it's the same if it's much lower or is much higher. So we're going to reject either on the higher or lower end. So this is a two-tailed test. So we'll have to write a rejection rule that would have where we would reject if our positive t-scores were over some amount or our negative t-scores were under some negative amount. Now the best way to do that is to do that in absolute values, because on the negative side, the higher the numbers following the negative sign, the lower the number. So in this case, we'll say reject HO if the absolute value of tcomp is greater than or equal to. Now here's where we finally use Excel to get this rejection rule number or critical value. So let's start out with Excel. The first thing we would do is we'd enter our data. I've entered the data for Clinic A in column A and the data for Clinic B in column B. And so first we enter our data. The next thing we do is we go up to Tools, and we go down near the bottom of the menu to Data Analysis, and we click on Data Analysis. Now if you don't have Data Analysis, you'll have to install it, and we talked about how to do that in an earlier lesson. So assuming you have Data Analysis and you click on it, you'll get this dialog box. Here we'll move our elevator button down near the bottom because the things in this dialog box are listed alphabetically, and we're looking for t-test, two sample assuming equal variance. And that's the type of t-test that we're using in this textbook. We use a number of different kinds, but for two samples we only use t-test two sample assuming equal variance, or we use the t-test paired for paired two sample for means. This is an independent sample, so we'll use the t-test two sample assuming equal variances. After we've clicked on that, then we'll click OK. Next comes up this dialog box. Here it asks us what our variable 1 is. And in this case, I'm telling it our variable 1 goes from A1 to A7. And our variable 2 goes from B1 to B8. Again, case doesn't matter. You could enter these in by typing it, or as we saw in earlier lessons, you could get these in these dialog boxes just by highlighting the numbers. So now that I've filled that out, the next thing I would fill out is I would put a check mark by labels. Because in my first row, which is A1 and B1, are the labels. It says Clinic A and Clinic B instead of numbers. And it's very important that I mark labels if I have A1 and B1, and if I really have labels in the first row. If I don't have labels in the first row, it's very important that I don't. We'll take a look at a little later on what would happen if we marked labels when we really didn't capture our labels, or if we don't mark labels. The next thing we want to do is check our alpha level. Now our alpha level is 0.05, so it's fine. If we were using a 0.01, we would change this to 0.01. The next thing is down there where it says Output Options. Right now, the radio button is in New Worksheet Ply. I like to move mine to Output Range. So you click the radio button there, and that'll take it away from New Worksheet Ply and put it in Output Range. Then it's very important for the next step that we click in the rectangle to the right of Output Range. We click right here and make sure that we have this flashing line. If not, whatever we type will go up in one of our variable 1 range or variable 2 range, wherever we type last, instead of where we want it to go. So we do need to click in this box before we start typing. Now I'm going to put where I want my answer to start. In this case, I think I'll start it in D2. So all that's left now is to click OK. And we should get an answer. But it's all shmunched together. And shmunched together is not good. So we want unshmunch it. The way we do that is we go up Format, we go to Column, we click Column, and then we go to AutoFit Selection. And we click AutoFit Selection. What that'll do is it'll make everything fit so that the writing isn't smunched up. So now we're doing pretty well, except everything is a little bit purple. We can click in any cell we want, any other cell, or any cell at all, and it'll make this purple go away. So I'm going to click up here, and now all the purple has gone away. Now let's look at these, what we have line by line. The first line I made red, shouldn't be red, but I made it red so we could see what line we're talking about. In the first line, it tells us the mean for each of the two clinics. So for Clinic A, it's 2.78 for the sample mean. And for Clinic B, we have 3.36. So their sample means differ. But that doesn't surprise us. We would expect the sample means to differ, even if they came from the same population. So that's not a big surprise. The next line is our variance. And we selected variance with samples with equal variances. Now these look like the variances differ quite a bit. One is almost 4 times higher than the other. But anytime we take two samples, even if they're from the same population, we're likely to get different variances, just like we're likely to get different sample means. So this isn't too surprising, but 4 times is a little worrisome. We'll talk about that a little bit later. Observations, it tells me that we have 6 observations for Clinic A. And it's real important that you check these. Make sure that you really do have 6, because it's easy to make a mistake and not grab all the data you wanted to grab. So in this case, we do have 6 observations. For Clinic B, we do have 7 observations. Note that there's not an equal number of subjects in each group, but that's all right. The pooled variance is the variance, it's kind of the average of the variances for Clinic A and Clinic B. It's sort of that. That's probably the best way to think of it. The hypothesized mean difference, in this class we always use 0. So that'll always say 0. It's possible, although we'll never use it in this class, to say does it differ by 5 or more, or does it differ by 3 or more, or 2 or more. So it's possible to specify some difference other than 0. But in this class, we'll always use 0. The next column, getting ahead of myself. The next column is our degrees of freedom. And in this case, we have 11 degrees of freedom. Because it's a total number of subjects, we have 13 subjects minus the number of groups. And we have 2 groups. So 13 minus 2 is 11. We don't even have to calculate that. Excel has done it for us. Next, the t-stat is what your book calls t-comp. This is a computed t-value, or the t-statistic. So in this case, our t-statistic, our t-comp, is negative 1.7770. The next row tells us the probability of getting a t-stat that differs that much from 0 if these two samples really did come from the same population, and if we were doing a one-tailed test. But we're not doing a one-tailed test, so we can skip that. The next is a critical t for a one-tailed test, and we're not doing a one-tailed test, so we can skip that. The next is our p-value, and this we will use. This is our p-value for a two-tailed test. And notice it's just double what it was for a one-tailed test. And so in this case, it's 0.1032 once I round it off. And we'll use that when we're doing our 7 steps. The next value is the one we're after now, which is our t-critical, our two-tailed test. So that, our t-critical value is 2.2010 if I round it. 2.20098 would round to 2.2010. So let's go back to our 7 steps. Let's take a look at where we are. Here we're looking for our rejection rule. We're saying reject HO if the absolute value of the t-comp is greater than or equal to. And so looking at our output, we see that that's that bottom row. And so we'll put 2.2010. So let's put that in our rejection rule. So reject HO if the absolute value of t-comp is greater than or equal to 2.2010. And you can see where I've filled those in our picture. So if we end up getting a t-comp that goes in either of those tails, we get to reject our null hypothesis, which is what we want to do. If we don't get it there, then we fail to reject. And that's not good. Let's take a look at what our t-stat was. Our t-stat was negative 1.770. Well, let's enter that into our step then. So our computation and test statistic, our t-comp, is negative 1.770. The absolute value of negative 1.770 is just 1.770. Now we can go back to our rejection rule and see what it says to do. It says to reject HO if the absolute value of t-comp, which we now know is 1.77, if that's greater than 2.20, is not greater. So this says we could reject it if it was greater, but it's not. So here we must fail to reject. The picture down below kind of shows you what this would look like. Our negative 1.770 is closer to 0 than our negative 2.2010. So our test statistic did not end up in either of the rejection regions. So here we fail to reject. So our decision is failed to reject HO. Now comes the most difficult part of the whole thing, probably for most students, and that's to write a good APA conclusion. And a good APA conclusion always starts the same way whether or not you reject the HO. It always starts out by stating your alpha. So here we would say 7, conclusion, at an alpha level of 0.05. They always start out that way. Now, the next part of the conclusion does differ by whether we reject or fail to reject. Let's assume that we had rejected HO. We don't, but I just want to do this as an example. So if we had rejected HO, our decision would have been reject HO, and our conclusion would be at an alpha level of 0.05, the mean force expiratory volume for 1 second for patients with coronary artery disease is significantly higher in Clinic B than in Clinic A. But how would we know B than A? Well, we can just look at our data and we can see that the Clinic B sample mean is higher. And if it was significant, then it would have meant that it was significantly higher. But it wasn't significant, so we'll have to go and look at it this way. We really failed to reject. So what we have to say is, at an alpha level of 0.05, there is insufficient evidence to conclude that there is a difference between Clinic A versus Clinic B in the means of the forced expiratory volume for 1 second for patients with coronary heart disease. Wow, that's a mouthful. And that's only 2/3 of that's 2 of the 3 parts we need for a conclusion. There's one more part we need to add, and that's what I call the statistical string. The first part of the statistical string is we say what test we used. In this case, we used a t-test. And then in parentheses, we'll put our degrees of freedom. Now remember what our degrees of freedom were. We can look here, our degrees of freedom from our output was 11. So in our parentheses, we put t, it's an italicized t, and then parenthesis 11 and parenthesis with no space. Then we put a space, an equal sign, a space, and then we look up at step number 5 to see what our t comp was, and we write that value. And even though we're going by the absolute value, we still put the negative sign here. It's very important that we do put it here. And then we put a comma, and then we put the p-value. Remember where we get the p-value. The p-value in our case is 0.103. We'll put p equals 0.1032. Now, if you hadn't used Excel, you wouldn't know what the p-value was, but you would know that since we failed to reject, the p must have been greater than 0.05. If we could have rejected, it would have been less than 0.05. But in this case, we failed to reject, so it must have been greater than 0.05. Remember how this works. As we first set our alpha at 0.05, that's the most we're willing to be wrong. And if we can reject the HO with a probability less than that, we do it. But if our probability goes over 0.05, we just can't afford to do it. So next, the next thing in our t-string is we tell everybody that it's a 2-tailed test, and we put that in parentheses. Now, not every test is 1 or 2-tailed. Some tests that doesn't really apply. But when it does apply, we try and tell the people what it is. Now, not all conclusions have to be written in 1 sentence. Actually, in most articles, you would say what your means are. You give a lot of results other than just this conclusive statement. But somewhere, you do need to say what the alpha level is. Now, sometimes a research article will run many tests. So it'll just say for all tests, the alpha was 0.05. And then it'll state each one separately without saying again what the alpha level is. But the first thing they need to do is say what the alpha level is at least once. And then you have to say what your decision is, and then you have to give the string so people know what kind of statistics you did end up with. This is what it looks like with all 7 steps all together. So we start out with our HO, our null hypothesis, then we have our alternative hypothesis, then we have our alpha, we have our rejection rule, we have our test statistic, our t-comp, then our decision. It's either fail to reject HO or it's reject HO. And then we have our conclusion, which is in these 3 parts. Now, I do have a few warnings that I want to go over with you. One of those is, and I mentioned we would go over this, when you're doing functions, instead of using this data analysis tool, you never include the cells that have the labels. You just tell it the cells that have the data. So that's easy to get into that habit when you come up to this data analysis, is to actually just list those that have the data. So in this case, the the cells that have the data are A2 down to A7, and then B2 down to B8. Now that's fine, but if you do that and then also check labels, then you'll get a funny answer. What will happen when you do that is at the top of your data, instead of saying Clinic A and Clinic B, what it'll say is it'll give your first data point. It thinks 3.23 is a label, not a number. It thinks 3.22 is a label, not a number. So it labels your columns with those. And it doesn't include them in the observations. So instead of having 6 observations per Clinic A, we only have 5. And instead of having 7 for Clinic B, we only have 6. So be very careful whenever you do this kind of analysis. Kind of look at your table labels to make sure that those labels match the labels you expect. If your labels are numbers, you've probably done it wrong. Another thing that might happen is you might put A2 to A7, B2 to B8, and then not include labels. A lot of people do that. They like doing that because that's the way they do it for functions, so they do it the same way when they're using data analysis. And that'll give you the right answers. The only thing it'll do is, since Excel doesn't know what to call each one of your columns, it just calls the first column variable 1 and the second column variable 2. And unless you remember what variable 1 is and variable 2 is, you can get confused. So I always like to include the labels, but you don't need to. You can run it this way, and it always works out just fine if you do that. So I think that's it for the labels. Let's see. Oh, one other warning. Here I mentioned that the variances here were quite different. There are ways to test your variances to see if they differ significantly, and if they do differ significantly, then you need to use the t-test assuming unequal variances. We don't do that in this class, but I just want you to know that when it gets up to 4 or 5 times as much variance for one as the other, then it might be problematical. I did test this for significance, and they aren't significantly different, but it still might be problematical, and it might be more conservative to do the t-test for assuming unequal variances. That's a more conservative test, less likely to be significant. Even with the same data, it would be less likely to be significant if you use that. But you're less open to criticism if you have variances that are this far apart. So that's it for this lesson. I know it was a lot, but I'm hoping it helped. Thanks a lot.